everyone. All right, let's get a few things set up here. First of all, can I have a captions? No go on captions. Seriously. They were working so well for weeks. What is up with captions and hating me? Okay, well, one moment, please, friends. Loafone, could you remove the closed captions tag then from stream? Because I guess my attempts at accessibility have just failed miserably. Thank you, probably Twitch. So, I'm sorry, friends. I'm looking into a couple of other third-party solutions for captions since these captions have been so unreliable. So please bear with me in the meantime, but I will, get... Ooh, okay, hold on. Give me one sec, love phone. I got you, friend. Hold on. Let's see, refresh the page. I've done that. I have the captions on. I have signed out, signed back in, refreshed, reset all of the various options I can use, all kinds of things, and it's not working. Loafone, I'm sending you the code, please. So, thank you. There you go. Thank you so much for taking care of that, by the way. And Ian Alex Hart starting us off with 2 dog treats. Thank you. I still need to figure out how to do a counter for those because that'll be a blast. So we will bank our treats as usual and then just give the dogs a whole lot of treats at the break. Let me make sure that I was loading the Furbo stuff ahead of time so that it would take less time when it is time to give the dogs treats. So it actually crashed. So there you go. More attempts for me to try to get things started. All right, but in the meantime, hello Strawberry Jesus, hello Dedaspot, and of course Ian Alex Hart. Hello Kavoth the Raven, welcome. Hi Justice Good Joe. Engineer Crew. Hi to everyone. Yes, for those of you who don't know, my area got what is for us quite a bit of snow, the most snow we've gotten in 2 years. And so that's been a blast because one of my dogs really loves snow. So it's been lots of fun. Oh good. Okay, the Furbo is loading. So then we will have that available as soon as we have time for a break. Okay. Well, so this is the second video now, or second stream in the Data Science Fundamentals series that I'm going to be doing. It's ongoing, so I don't have like this strict planned schedule that I did for Machine Learning Miss. So we're going to be doing a new topic pretty much every Sunday. If you all have any topics that you'd like to request specifically that are kind of, fundamentals of data science themed, please let me know and I will do my best to make sure that it gets to be part of the series. But tonight we're going to be kind of building on what we talked about last week. So last week we talked about exploratory data analysis, or EDA, which is a really important part of preparing your data for a model. And today we're going to dive into a couple more aspects of data preprocessing. And so we're going to talk a little bit about scaling because we had some questions last week on scaling. And since I think one of the themes of the 12 Days of Machine Learning Miss was scale your data, I want to tell you about a couple of different scalars and what they're doing and how to pick a good scalar. And then we're going to move on from that to talk about dimensionality reduction. And in particular, I'm going to show you a really, really popular method for dimensionality reduction, say that 5 times fast, called principal component analysis, or PCA. So once we go through that, I show you how that works. Then we're going to move on from that to show kind of a classification model that I didn't have time to show you in the 12 Days of Machine Learning Miss, but builds really kind of intuitively from PCA, and that is a support vector machine. And so those are our topics for today. Lots of acronyms: PCA, SVM, but hopefully at the end of it, you all will be experts. All right. And thank you, Tiger of THT, for following. Welcome to the stream. And Kavath the Raven, you say, thank you so much for this series. You're about to start a data science bootcamp, and you're so excited to hear someone knowledgeable talk on the subject. Well, you are absolutely welcome. I'm so excited to be able to bring all of this series, all of these topics to you, and hopefully through the endless weeks of the Data Science Fundamentals series, by the end of it, all of you will be experts too. So it's going to be great. All right, I need just a second to get our whiteboard up and running here. Hi, Lord Azazel. My whiteboard's literally called whiteboard. Wow. All right, that was a little bit of a brain fart moment. I'm sitting here going, what's the app called again? Oh, and that is very blue. Okay. Okie dokie. And for those of you that did miss last week, do not worry. The VOD is already on YouTube. And in addition to that, the code and the notes from last week are up on GitHub as well. And hi, Mediocre Gamer. Okay, so let's switch gears here. And we have our whiteboard. All right. Hopefully I don't break it, because I often do that. All right, there we go. And I need my pen. And yep, Tiger. So that's one of my degrees. Or I guess I left graduate school early, but that is one of my academic experiences, shall we say. So let's start off today. Oh, and I scrolled all the way down through my notes so I could tell you all the things we're talking about, and now I'm at the very end. So today's going to be a little bit different. Because typically I do kind of like all of the Blackboard notes at the beginning and then we do the code, but today it's going to be a little bit more integrated. So we're going to be switching back and forth between coding and talking about things on the Blackboard. So we'll see how it goes. But all right, so we are talking first about data preprocessing. All right, and what do I mean by this? Well, preprocessing actually includes a lot of the steps that we talked about last week. So, oh no, it's very thick. There we go. So when we're talking about data preprocessing and as kind of a step in your EDA, in your exploratory data analysis, does anyone remember the stuff that we talked about last week, or just you already know because you're an expert, what kinds of things you do when you're talking about preprocessing your data or preparing your data for a model? What do you do? Does anyone have any clues? Do they have any ideas? Also, I gave the answer away earlier. I gave one answer away at least. So there's a free one. Filtering. Okay, just as good, Joe. What do you mean by filtering? Give it a good wash behind the ears with soap. Not quite, Generic Crew. And Strawberry Jesus, yes, you have picked up on the thing that I mentioned earlier, which is scaling our data. So we might scale. What else might we do when we are pre-processing our data? So there's a lot of things that we can do to the data to get it ready for modeling. But start to think a little bit back to last week, and we talked about some of these steps and some of the challenges that you might run into, or some of the problems that your data set might have that you might have to deal with. And if you think about that first, like think about the problems you might run into, it'll give you a clue as to what pre-processing steps you need to do. Okay, so looking for NANs. Yeah, so looking for missing data. So we need to handle missing data, absolutely. Now, handling missing data is a whole bucket unto itself. So you can do a couple of different things here. We can fill with, I would say, an extreme value is what I'm gonna call it. But that means a value that is so different from the rest of the data set that you know it's missing. You can fill, I've seen people fill with 0. You can fill with one of your measures of central tendency, so something like filling with the mean or the median. You can also do, and I talked about this last week, so I'm just going to remind you, you can also do something called imputation, where essentially you use a model that you kind of it's like modelception. You're gonna model within a model, but you're gonna use a model that fits to the feature that has, you know, missing data, and then you use your model, if it has good performance, to fill in the missing data for you, and that's called imputation. And Z last, if you say removing missing variables, that's excellent, thank you. That's the other thing you can do, is you can drop missing data too. So you can just simply remove it, drop it or remove it, same thing. Okay, so what else do we do with our pre-processing? And we'll talk about scaling. So you might be like, oh, we just went into all of these different things for missing data, but there's different kinds of scalars. Well, have no fear. That is literally the first thing we're going to be talking about. So I'll go into different kinds of scalars that we can use and why you might use different ones. But what else do we do in our data pre-processing? And for this, you might think back to maybe our Titanic data set. Yes, okay, just as good, Joe. Again, reading my mind. Yes, and how do we deal with categorical data? So we need to deal with categorical data. And what might that entail? I love when that happens, when I'm trying to like lead people to think something and I haven't even opened my mouth really, and just as good Joe is just there, like, yep, I already know the answer. Okay, so yeah, Strawberry Jesus, you say one hot encoding. Yep, and so you can do one hot, or you could do dummy variables. So essentially what you want to do with this is you want to take it from being a category, so having a string, to being a number. So having for each, typically how you do this is for each category that you have, you add a feature, you add a column, and then you substitute for that whether or not that line or that entry belongs to that feature. You have a 1 or 0. And that was a terrible explanation. So actually I'm going to draw you a little picture. So instead of having a feature that's, say, gender, right? And we have male, female, and like non-binary, right? So this is our gender column, and this is like data 1, data 2, data 3. What we want to do is we want to take these categories, which obviously our model can't take, and instead we would probably convert them to, something like this. And my head's going to get in the way, so hold on. Always happens. Right, and so for this one, we would have a 1 here, 0 here, 0 here. For this one, we'd have a 1 or 0, 1, 0, and for this one, we'd have 0, 0, 1. Now, one thing that you can think about is, and thank you, Peldies, for following, is that for some of your categorical variables, it actually, so far more often, unfortunately, people aren't very progressive, and they're not going to have this like non-binary option, which poop on them. But if you think about it, if you have a binary category of some kind, like gender when people aren't being progressive, let me pick another color, yellow. Really what you're encoding, when you're encoding one of these columns, you're encoding the other. And so really, why make 2 columns? Instead, you could just, because you have 2 options here, right? You already, like here, if we get rid of this column, and instead this alone, oopsies, there we go. This alone encodes all of the information we need, because if it's a 0, we know male, and if it's a 1, we know female. And so that's another thing to consider when you are doing that dummy variable like substitution, or you're doing one hot encoding, is can you drop one of the categories without losing information? So it's a way to simplify. And actually, I played Among Us last night. So I was streaming last night. I was doing a panel in the evening for accessibility in games, and then we played Among Us. We played Among Us after that. And then Thursday, I think, was the last stream, and that's when I was doing game dev. But in any case, so, let's see. I guess the other thing I'll put in here that you might need to do is to handle noise in your data set. And so this can mean a lot of different things. And I'm more setting up a future stream here. So we're not going to dive too much into it. But noise in your data set is kind of like clutter. You can think about it like that. And so if you have very noisy data, it's going to be really, really hard to fit a model. However, when you attempt to reduce noise in your data, you can sometimes lose information. And so that's a trade-off that you have to deal with. And noise can literally mean, like, if you work with audio or visual data, that can literally mean audio or visual noise as well, on top of, you know, what we consider more of like the traditional data noise sources. Okay, so let's dive in a little bit. Oh no, I'm moving things. I'm ruining everything. Okay, there we go. The crisis is averted. So, when your data starts screaming at you, generic crew, if your data's screaming at you, I don't want to know what you're doing. That sounds like not a good situation. All right, so let's talk scaling a little bit more in depth. I know, and I'm going to put a little heart here because scale your data, friends. More often than not, people do need to scale their data and they don't. So especially when I'm coming in and I'm helping someone who might be a little bit new to machine learning and they're asking me, why is my model just doing terribly? Preprocessing is one of the first places I look, is like, what EDA did you do? So looking at the relationships between your variables, looking at, you know, statistical measurements of your variables, their distribution, and then depending on your model type, but for most models, scaling your data. And this can make a massive difference. So for example, like I've seen a jump of 30 to 40% in accuracy for a classification model between scaling and not scaling. So scale your data, scale it. Anyway, now that I hopefully have impressed upon you the importance of it, what does this even mean? What does it mean to scale your data? And really what this is talking about, oh, I still need to change the generic query. I need to change the GitHub response there. The repo URL there is completely correct, but it says the code for ML-ness can be found there. The code for everything can be found there. So the code that I work on for all the game dev projects is there, as well as the code for machine learning miss and for this series as well. So I need to change that Nightbot thing for all the things, all the code. And see, last one, if you say scaling or normalization. So those are two different things, but sometimes people will do both, or sometimes it's sufficient to just normalize. But in this case, we are going to talk more broadly about scaling. And so what do I mean by scaling? Who knows? Who has the answer? What even is scaling? Oh, thank you, Loafman. You fixed that so fast. And you didn't do like all your base joke, which I would have done, but that's fine. That's probably more professional to have that be my note. Okay. In any case, who wants? Oh no, did my mic? Okay, my mic didn't break. This mic is so finicky. Those of you who've been here for a while know that it is just like prayers and rituals and spells go into hopefully just like keeping it together. And if I bump it, I panic. But what is scaling our data? What are we talking about? Okay, so Dennis Bot, you say you don't know, which is totally cool, but maybe it has to do with roundings. Not quite, but that's, I could see if you had a data set where really like the decimal values didn't matter and you were trying to save space, you could consider converting from floating point to integer, but, and just as good, Joe, yes, so you say, ensuring things are on the same scale or level so they can be comparable. Yes, and so what we're going to be talking about tonight is something called per feature scaling. And what that means is that we're going to scale each feature. And the goal of per feature scaling is that we want our features to be comparable. I like the way that you said that. So this ensures features can be comparable. It also ensures that each feature is contributing to our model in a way that is like proportional to that feature's importance. And by that I mean, and I've given this example before, but let's say that I have a data set. I think we ran into this with our Spotify data set. But if we have a data set that, say, spans 50 years, and but we have another variable that is the song length, right? So maybe if we look at the range of those two features, the range of years and the range of song length difference, the range of years is clearly going to be greater. But it might be that like a difference of 1 in year makes a lot less of a difference than a difference of 1 minute if we are measuring our song length in minutes. And in that case, what we have is we have kind of like, we're not really able to compare them well, because it's going to look like one of these features is far more important, say year, because it has a wider range and a larger value. And so scaling puts everything on the same level so that the features that are actually important really do kind of rise to the surface, and we can figure that out, we can extract that importance, but then also make sure that our model isn't overfitting to features that have, because it isn't overfitting to certain features just because they have a wider range or because they have a larger value. When really, if you think about, like, we're going to talk about this a lot tonight, but the difference between the value of the feature and the information of that feature. And so the value of that feature might be large, but that doesn't correspond to an increase in like the information that that feature has. And so for that, we need scaling. And does anybody, here's like a bonus question. I wish I could give like extra credit or something. Does anyone remember the scalar that we've used previously in the 12 Days of Machine Learning Myths and possibly last week? We scaled our data last week. I think we did. Does anyone remember? Nope. Oh no, Justice Good Joe. I don't think you've gotten anything wrong ever. Nope. So we used one that's called Standard Scalar. Yes, Strawberry Jesus, exactly. So this is from, this is in scikit-learn. The scikit-learn library for Python. And so we are going to talk about min-max though, so have no fear. And all right, Ian Alex Hart with 2 more dog treats stacked up for the pups. Okay, so actually we'll start here. So one feature, and I'm not going to go through all of them. I will actually post a link in chat to a really, really great like documentation that scikit-learn has on a bunch of their different scalars. And I don't want to go through like all gazillion of them because that's just not helpful. They have some really, really great visualizations though, and really, really good explanations of each of the scalars. I'm going to go through, how many did I put here? 1, 2, 3. I'm going to go through 3. And these are 3 of, I would say, the most common ones that I've seen in use. So the first one obviously is standard scalar. And this is a per feature scalar, right? So we're going to scale each feature. And the way that it does this is it gives each feature the same mean of 0 and variance of 1. But since this uses the mean, what is this really sensitive to? Who wants to tell me? Because our scalars are going to be sensitive to different things. Yes, Justice Good Joe, exactly, outliers. So this is sensitive to outliers. All right. And what that means is that if your data set is full of outliers and you don't want to remove those outliers, then standard scalar might not be a good choice because it's going to struggle with giving the same balance when there are a lot of outliers. Okay. I don't know why I put parentheses around here. Can I do it? Oh, yeah. Okay. It's the little things. All right. So as Justice Good Joe mentioned, we also have the min-max scalar. And hi, Professor Saucecat, welcome. And welcome, Verfolger. Thank you so much for following. Okay, so min-max scalar squeezes our features so that the range is 0 to 1. Is this sensitive to outliers? And why? Well, just as good, Joe, you just used this, so maybe you know as well, but what do you think? Think about kind of like think about the measures of, not just the measures of central tendency, but the statistical measurements that are being used by each of these scalars, right? So here, the clue was we're using mean, right? Which is really sensitive to outliers, and so that makes our scalar sensitive to outliers. Here we're using range. So what do you think? Is it gonna be sensitive to outliers? And hi Toasty, welcome. And hi Albel. Yay! I haven't seen some of you in so long. Welcome back. It's good to see everyone. Welcome. I know, Albel. Yay, right? Gotta have some fun. I get round 2 of my vaccine tomorrow. So I gotta get all up in my fire station uniform and trudge out to headquarters at what feels like the crack of dawn for me, which is like 8 a.m., but still. Can you turn your mic around? The audio is upside down. What? I don't know what you're talking about, but my mic is right side up. Okay, and just as good, Joe, and Professor Saucecat, you are absolutely correct. It is indeed sensitive to outliers. And so really, and this is a perfect case of a time when I feel like sometimes your intuition might be to memorize. And yay, Ian Alex Hart, thank you so much for more dog treats. So our dog treat count is now up to 6 dog treats. And so at the break, we will be stuffing the dogs full of dog treats just for you all. But okay, so what I was saying is that the intuition might be to just memorize this and memorize, okay, standard scalar is sensitive to the mean. Okay, min-max scalar is sensitive to outliers, and min-max scalar is sensitive to outliers. But you're doing yourself a disservice when you just memorize kind of associations here. Because really, think through it kind of from first principles, if you will. Like, we've talked about in previous streams how the mean, as kind of a measurement of the center, can be very sensitive to outliers and can be affected by those outliers in a way that isn't really helpful statistically. And so it makes sense that something that relies on the mean itself would be sensitive to outliers. Similarly here with the range, the definition of range is literally the maximum minus the minimum. So if you have outliers, your minimum and your maximum are going to be skewed. Whether those outliers are, they tend towards, very, very negative compared to the rest of your data, or very, very positive compared to the rest of your data, you're going to have a much, much wider range. So absolutely, something that relies on the range, which is itself sensitive to outliers, would be sensitive to outliers. And so, Ship Shoop, thank you so much for following and welcome to stream. So that's more how I want you to think about it. And if I say something while we're going through this that's like, oh, well, this thing does this other thing, and you're like, I don't know. I almost imagine people writing it down, even though you should just enjoy stream and not take notes if you don't want to, of course. But if in your head you're like, okay, I'm just gonna memorize that, stop and think it through. And if it doesn't make sense, say something. Because the benefit of all of you being here, all of you wonderful humans being here with me, is that this isn't a class. I'm not some teacher who has to cram through to get my curriculum done or something. I'm here so everyone understands what I'm talking about. And 2, we're hanging out. This is casual and this is fun. And so if something doesn't make sense, I'd so much rather have a conversation about it and explain it better for you than run the risk that everyone is just kind of nodding and going along with it. And let's see, Lord Stealth, thank you so much for following and welcome to the stream. And let's see, Generic Crew, you say, should we throw paper airplanes at the teacher? Now that would be cute if there could be a redemption that would put a little paper airplane flying across the screen. I could be down for that. Okay. And so, Strawberry Jesus, you ask, how is min-max working mathematically? Sure. So let me remember myself. Hold on. So first we get our standard deviation, okay? And our scaled value for, let's say, a given, I'm going to call it x, okay? So for a given x is going to be the standard deviation times, what is it? The max minus the min plus, hold on, max plus the min. Max minus min plus min. Yes. Okay. There we go. Value minus min, max minus min. So for this, and then for standard deviation, that is, sorry, oopsies. In this case, that is the value. So actually, I shouldn't use x here. So let's just call it, crap, hold on. This is x scaled. This is our initial x. Minus the min all over the max minus the min. So I think that's what you're talking about, Professor Saucecat. And that here is how they define their standard deviation. And then that they multiply by the range, right? This is just our range plus the min. And Candy Cane 20, you say if both are sensitive to outliers, how can you handle the outliers then? Well, there's a couple, so I will tell you, don't worry. We have one more left to talk about that, spoiler alert, is not sensitive to outliers. But so you can if you are concerned, let me restart that. If you need to keep your outliers in your data, use a scalar that is not sensitive to outliers, like the one we're just going to talk about. If you have outliers in your data, but you don't really care about them, you can remove the outliers, and then you can use a scalar that is sensitive to outliers. So you kind of like, you can have a choice. And so just as good, Joe, you say, when would we want standard scalar over min-max scalar? So this is really interesting. And actually, before I answer that, I have a link for all of you. So give me one sec. Come on, I put it in my notes just so that all of you would have it. Hold on, because it's really, really great, and I want to make sure that I don't forget to give that to you. So, here we go. There it is in my notes. Wow, I put that completely in the wrong place. Here it is. Okay. All right. There you go, friends. And so in this is some great documentation about the effect of different scalars on data. And so sometimes things are personal choice, and sometimes it is a little bit like, how to explain this? At least for me, there are definitely going to be data sets where I don't want to compress everything into a 0 to 1 range. And then there's times where, that doesn't matter whatsoever. I'm actually going to show you in a moment, once I get through the robust scalar, spoiler again, is the next one we're gonna go through. I'm gonna show you the effect of these three scalars on some data. Hi Diatomes Attack, welcome. I know, right? I love it, it's so pretty. With me returning to the fire department, I can't have fun hair because it's one of my uniform standards. So if I am an operational active operational member, I can't have funky colored hair. So alas, I have to resort to wigs, which are still very fun and cool, and I love them because it at least gives me the freedom to still, have the fun colors without, having to sacrifice the fire department. Gotham Geek, welcome and thank you for following. Okay, so the last scalar we'll talk about is the robust scalar. And so this is great. This is not sensitive to outliers. It ignores outliers because It basically is like standard scalar. It's kind of, this is real specific, Jess. Kind of like standard scalar. Except instead of using the mean and the variance, except it uses the median, which we all know is not sensitive to outliers, and it uses quartiles. And so this allows it to be insensitive, to be like, impervious to outliers. However, it does mean that these features, the features that once scaled with robust scalar, will have a larger range than with other scalars. So, oh, I need my purple, not sensitive to outliers. Okay, so with that, let me show you some code. Give me 1 sec here. I'm just gonna switch to this so I can get our code up for us. And go. Oh, that's bright. And we want that 150% for everybody. And okay, so let me show you what this looks like in practice. So we've got some imports to do real quick here. I think I used Seaborn at some point. I have it there. Probably means I use it. And then I'm going to copy these because I hate having to write them out every time, but these are just some prettiness settings. Stuff that just makes the figures look better for when we do our visualizations. Okay, so the data set that we're going to be using tonight is this breast cancer data set. And so what it is composed of is, give me a sec to write this out and I will show you actually. What is it? Feature names? Is that what it's called? I think that's what it's called. I don't often, like in my everyday experience, use these preloaded data sets because usually I'm using yeah, it's feature names. Usually I use raw data that's icky. And yay, Ian and Alex Hart, thank you so much for 2 more dog treats. So we're up to 8, I think now. All right, so here's what our data looks like. And really what we're looking at is lots of, I'm not a cancer doctor. What is it? Oncologist. I'm not an oncologist. But I believe these are, different features of tumors. So these are the different measurements of, these are different measurements related to tumors, and then we have whether or not they are malignant or benign. And Strawberry Jesus, you say outlier detection like local outlier factor and removing outliers works too, right? It really depends on your situation, and so that's kind of a per project decision, and that's because there might be cases where you can't remove outliers, like say a cancer data set, right? We really need to create, let's say we work for a medical company and we need to create a classifier that is going to be really, really, really good at detecting, cancerous tumors. We can't just get rid of our outliers in that case because we would be introducing a restriction or a limitation of our model. There's cases where you absolutely can remove outliers, but this data set doesn't have like a whole lot of outliers, so we're going to be great. it really depends on your data set and the goal that you're trying to achieve with your model. So, but you're right, like if you wanted to use something like standard scalar or min-max scalar, and you knew that you didn't need your outliers, you can absolutely identify them and remove them. Mr. Euro, thank you so much for following. And Sympathy, okay, wait, no, it's a raid. Hold on, I gotta be good. I've gotta wait for the raider to enter chat like a responsible person. Hi, Sympathy, thank you so much for the raid. Welcome, raiders. Welcome to stream. Welcome to Science Sunday, where we talk, sometimes we talk astrophysics, sometimes we talk machine learning and data science. Tonight is machine learning and data science. So this is the second stream in my data science fundamentals series. If you are just really wanting to learn all about machine learning, I would also encourage you to go to YouTube, because I have the 12 Days of Machine Learning Myths on YouTube, where we went through 12 different machine learning topics. It was awesome. There's code, there's notes, it's beautiful. There's like, look at this, like fun notes that we do. We'll come back to this in a moment. And we also do code, so it's great. And let's see, Vacillate and Mr. Box Monkey, thank you so much for following. And welcome. And V Galvez, thank you so much for the sub. Wow, 3 months in a row. That's awesome. Thank you so much. And thank you for supporting the stream. But let's see. Hi, Shadow Fungi and the Cheshire Chameleon. That is quite a name. Welcome everyone. So tonight, to give you all, actually, to catch you all up, tonight we are talking about a couple of different topics. So I've started with talking a little bit about data preprocessing, which is a step where we get our data ready for a machine learning model. We briefly talked about scaling and 3 different scalars in the scikit-learn library with Python that are really, really useful, and each have like their pros and their cons. Now I was going to show, I have too many things open. Here we go. I was going to show an example of how these 3 different scalars work. And I'm excluded. Thank you for following. Once we get through this, we're going to talk about something called dimensionality reduction. And so this is where, if we have thousands of features in our data, like, oof, that's going to get really nasty. We want to talk about how to reduce that number without losing too much information. And Stratzy, thank you for following. Yes, give Sympathy a shout out, please. I hope your stream went well. What were you all doing? Was it a good stream? And then after we talk about PCA, which is principal component analysis, that's an approach for reducing dimensionality in your data. We are going to, I'm gonna tell you all about a classification machine learning model called support vector machine, and we're gonna build one, and I'll show you how it works. And it's really cool. It's very intuitive. So if you haven't done any machine learning, this is a great stream to walk in on, because we're not doing anything too fancy today, but you get to learn a lot of different things. So welcome. Okay, so what was I doing? Right, we have our cancer data set, and what I'm gonna do for the sake of showing you how the scaling works is, because we have, if I remember right, we have 30 features in this particular, ooh, look at me, I'm just gonna use 2 of them so I can plot them and I can show you how those features change. And Z-Last Wolf, you say, can we use SVM instead of PCA? So these two, SVM and PCA, are trying to do 2 different things. Principal component analysis is a way that you can reduce the dimensionality of your data. And it's going to result in things that feel a lot like SVM. That's why I'm talking about them both today. SVM, however, is a model. So that is a model that is going to try to predict something. It's a classification model. So we're going to be trying to predict a label or a category. And so you wouldn't use one instead of the other, because they're really trying to accomplish different things. You can use them together, but they are 2 categories. Like PCA is in our pre-processing stage when we want to reduce our dimensions. And then SVM would be a model that we would choose. If those of you who were here for the 12 Days of Machine Learning Myths No, we also did, what did I do with all of you? I think for classification models, I probably showed you decision trees. That's such a like intuitive way to classify. What else? Does anyone else remember what I did? Oh God, I can't even remember. Well, that was like over a month ago, but we also did some other classification models. Hopefully somebody that has better memory than me can remember what we did. Oh my gosh. I can't even remember. Yeah. We did decision trees because then the next day I talked about ensembling and random forest, but I could have sworn there was one more classifier that I showed you. Nope, it's fallen out of my brain. All right, well, the code is there on GitHub and the VODs are there, so past me can tell you all about the thing that present me has forgotten what we did. But all right, so we are gonna use just our first, what first? Yeah. No, but I wanted them to be very, very different, so that's why. Yep. Okay, so we're gonna use columns 1 and 2, 2 and 3, depending on how you're counting. The mean texture and the mean perimeter. K nearest neighbors, that's right. Okay, thank you, Strawberry Jesus, for helping me out with that. Ooh, all right. So now we're gonna import our standard scalar, our min-max, I think that's capitalized, scalar, and our robust scalar. These are the 3 that we just talked about. And one Firkin, thank you so much for following. And Generic Crew say, you heard K nearest neighbors we're finding our neighbors again with AI. Well, you are finding your neighbors with AI if you are a data point. I mean, because anyway, I was trying to be silly there. And so, give me 1 second. Okay, and then Strawberry Jesus, you say, what are your most used ways for dimensionality reduction besides PCA? So you can use, there's a couple of other approaches. You can use autoencoders. You can do manifold learning. You could do something called matrix factorization. Not talking about those tonight. I had originally planned to, and then when I put a lot of that content in the stream, it just got way too long. So we could talk about those another day. So if that's something you're all interested in, we could do a deep dive into dimensionality reduction, and I could talk about a whole bunch of different ways to do it. But it was a little out of the scope for what I have time for tonight. Ian Alex Hart, thank you so much. 2 more bits, 2 more dog treats. So I think we're up to 10. Thank you, Loafbone, for keeping track. It's gonna be so good. The dogs are gonna love this. So once we're through talking about scalars, we'll give the dogs those treats. Because if I wait too long and we have too many treats, and then they're just like not hungry anymore. So these dogs are being spoiled, Professor Sauce Cat, and they love it. So, okay, so we're gonna do a scatter plot. And first, I'm gonna show you, what was the other one, mean perimeter? Yeah. And what limits that looked good? Oh yeah, here we go. So this is what it looks like without scaling. What? Mean texture? Oh. There we go. So this is just 2 data points. Like, we're not trying to fit anything to this. This is not the full breadth of our data set. We're just looking at 2 features and how our 3 different scalars will affect them. So, just as good, Joe, you say there's a really cool representation learning with graph paper that you could share on Discord. Talks about ways of dimensionality reduction and encoding. Ooh, that sounds really cool. Yeah, please do share that in the Discord. We now have a machine learning channel just to talk about all this cool stuff. And so this, all right, so this is what our features look like right now without any scaling. And so first, let's And Lord Leiden, thank you so much for following. Welcome to the stream. So now, first we're going to use our min-max scalar. And then let's take a look at what it did. Okay, so you might go, oh, I don't know, it doesn't really look that different. Well, if I were to put the same limits on, one, it's going to be really hard to see. You'll see that absolutely things changed. What? These are the same axes, okay, same range, and all of our data, like we talked about, has been compressed between 0 and 1. And Seska is online. Thank you for following. Now here's the thing. Notice what hasn't changed. The data themselves, like the relationships between the data, haven't changed. We've just shifted them. We've just changed the scale. And so that's really, really important, because these transformations they should still preserve the relationships, preserve the information that we're interested in exploring with our models. They're just changing the scale, right? They're changing, you can almost think about it like a microscope with magnification, right? They're changing the magnification. And so let's do our robust scalar. What did I call the data? Yeah, all right. And then we're going to do the same scatter plot. So similarly, you can see here, again, all of our relationships are preserved, but here we've got a range that seems more like, -2 to 4, and then, yeah, -2 to 4. And so, and let's see, Lordly Dawn, you say, what is the purpose of it? Does it make it easier to work with data with smaller values? So it's not necessarily that it's easier to work with that data, but that we can be assured that each of those features, when each of those features is kind of on the same scale, we know that one feature might not disproportionately skew our model. And so this is because if you think about it, a model is just looking, how to explain this? It's just looking at the numbers. Our model doesn't know that a year of 2000, well, it's just a year, So it's not really 2000 the number. It's not 2000 of something compared to the example I was using earlier was a Spotify data set that we used. The difference between a song that has a change of 1 minute might be vastly different than a change of 1 year, right? A change of 1 minute in a song might have a lot more meaning than just a difference of 1 year, even though those are both changing by 1. Similarly, we can't say that, a song that had a release date of 2000, that 2000 is somehow, it's 2000, it's so much bigger, and that's so much of a larger number than a song length of 5 minutes, so that 2000 has to be more important, right? Not really. It's 2000 it's just a year, but to the model, that's going to represent 2000 the number, and that number is going to get compared to all the other numbers that we're feeding in. And so actually, you know what, just as good, Joe? One time that I might use min-max scaling specifically instead of standard scalar is if you have a very sparse, if your feature vector is sparse and you're dealing with a lot of categorical encoding, because you're going to have a lot of zeros and ones, so it makes sense then to compress your continuous features in that case to 0 as 1 as well. I was still processing your question from earlier, but by scaling our data, we're ensuring that our model's actually going to fit to the relationships that each of these variables has with the other, instead of accidentally getting skewed because they have different ranges. They have different distributions. Hopefully that answers your question, Lordly Dawn. But now let's see, we are missing standard scalar. So I will show you our standard scalar as well. Call it scale test. So similar now, you can see we've got, I think, -2 to 4, or possibly -3 to 5. So a little bit of a wider range. But again, like, I think visualizing it really helps because you can see that the relationships between each of these data points, those are preserved. We're not changing that. When you scale your data, you're not losing, information. You're simply, I like the metaphor of thinking about it like changing the magnification. You are just fitting everything into the same range. So, and it will lead to way better model performance for a lot of different models. Like I mentioned earlier, I've seen 30 to 40% jumps in accuracy just from scaling your data. Backyard Expedition, thank you for following. Okay, so actually, this is a great time since we're gonna switch back to our Blackboard and we're gonna talk about dimensionality reduction. This is a great time to give our dogs some treats. Let me get that set up really quick for all of you. I had it loading in the background, so we should be pretty good. Let's see if we can get the dogs to come out. So what? We've got 10 dog treats banked. So here's Hubble. So Hubble really wants to go outside. I don't know if you all could see, but we got some snow all day today. And Hubble loves the snow. He is a snowy boy. There we go. So here's one treat for Hubble, unless it spits out 2. We'll count it as 1 because he's a good boy. Oh no, did it not shoot out a treat? Let's see. Oh my god, the head tilt. I love when dogs do that. They like tilt their heads because they're very cute. Oh no. Is it not spitting out treats? I'm sorry, Hubble, I'm trying. You can see his toy in the background. I've talked about this toy, his Clever Pet. So this is another, it's jammed. Okay, holds please. Technical difficulties, friends. We will be unjamming the Furbo and then we will return to give treats. And oh no, how do you say your name? How Paulo? I'm really totally crap with names. I'm so sorry. Thank you for following and welcome to the stream. Oh, come on. There we go. All right. So while we're waiting on the Furbo, let's see how much. This isn't going to take too much, so I will put it below here. I can at least start us on talking about dimensionality reduction. I know, Kitty Slayer. I'm sorry. We're having to wait. The silly Furbo gets stuck. It gets jammed. It gets a lot of use though, and the pups really love it. So I'm honestly surprised. I'm very grateful to all of you wonderful subscribers and people who donate, because it really was through all of your donations and subscriptions that we were able to buy the Furbo and make this part of stream. So thank you all. Okay, we'll just set this up. Just let me know, Loafbone, when it is all set. Dimensionality reduction. Okay. I can try again. All right, let me try. Hold on. I know both of them are waiting. Okay, boys. Very good, boys. Now we've got both. Let's see if it'll work. Oh, they reacted. So I think, yep. Okay, I just shot. It just shot. All right, so we've got one. That was one treat. Oh, they're such good boys. Let's see. Good. 2 treats. And hi, Call. I'll answer your question in just 1 sec once we finish giving the dogs treats. 3 treats. I love it so much, their excitement for treats. Hubble is a big boy, so he's about 70 pounds. So when I adopted him, they just knew he was part border collie. And so 6, they said, you know, he'll probably get like 40 pounds. Oh my goodness, Ian Alex are adding more dog treats. So now we're gonna give them 12. All right, so 6, 7. He caught it. Oh wow, okay, I missed that. Good for him. Good job, Hubs. 8. But yeah, so they told me he was only gonna be probably max 40 to 45 pounds. He hit that within like 3 months. And I was like, oh no. And so I used, there are all of these curves for like dog size. So you can look and you can kind of start to plot at different ages your dog's weight and what it predicts their end weight. So I am very glad that he seemed to grow very fast and then like sort of plateau, because at least those curves, he was supposed to be, according to those curves, between a German Shepherd size and a Great Dane. And at the time, I was living with my parents, and my mom was only okay with me getting a dog if it was a medium-sized dog. She still maintains Hubble as large. I think he's a medium-sized dog. But she was definitely not happy with at the time how large he became. And I was like, oh God, if I end up with like a 120-pound dog, like she's gonna get so mad. But I mean, that's the, honestly, it's the joy of rescuing, is that you really don't know what you're gonna get. He's perfect sized, exactly. Okay, so that's, I think, 10. All right, 10. It might be jammed again. I'm gonna try one more time and we'll see. He's waiting so expectantly. Let's see. If he does his little head bob. Okay, I think it's jammed again. So for Ian Alex Hart's last 2 treats, we're gonna have to wait. So we'll fix the Furbo. D. Why did I take off my glove? I'm going to be writing more. He had way more than 12. Okay, well, you know what? I say it's 12 Furbo treats. If the thing shoots out 2 at a time, I mean, that's just a bonus. And Randall Apocalypse. Whew, I don't know why that was hard. Welcome, and thank you so much for following. But okay, really quick. So I had a question earlier. Call, you say, what's up? You're a game artist. You want to dive into some coding for C++. Do I have any recommendations? I don't know C++. So I would recommend, I've got channels in my Discord for folks that are interested in different languages. So you could definitely kind of jump in. We've got lots of game devs, I feel like, in Discord. You can also check out, and Loafbo, maybe you can help me with this. Can you give a shout out to Jessica Mack into Twitch? She's a game dev who does C++. She's actually building her own game engine in C++, and she's amazing. So I would definitely recommend following her, and she might have some good resources for you. Myself, I don't know C++ and I don't use it, so okay. And let's see. Strawberry Jesus, you say, can you please clarify the difference between normalization and standardization, or is it the same thing essentially? So here's the tough thing. Yes and no. So people use them interchangeably, but technically they refer to different things. So normalization is your min-max scaler. So that's scaling your data to range between 0 and 1. Standardization is transforming your data so that it has a mean of 0 and a standard deviation of 1. So doing different things, but here's the crappy thing. People use them interchangeably. So it really is like it's difficult because it's like you have to kind of ask for clarification, because some people use them to mean the same thing, one or the other. But technically speaking, they are different. And so it's a communication issue, I would say, where if somebody says that, like, you kind of have to follow along and see what they're actually talking about. So hopefully that helps, Strawberry Jesus. I myself run into that trap as well of accidentally using them interchangeably. So if I do that, feel free to call me out and have me clarify. But okay, dimensionality reduction. What are we talking about? Dimensionality is such a fancy word, right? It feels fancy. What's dimensionality? Well, we're running into something that we talked a lot about during Machine Learning Myths, which is that a lot of times we use words that sound more complicated than they really are. And dimensionality is one of them. Yes, it's fun to say. It makes you sound really, really cool to say, oh, dimensionality reduction, instead of literally just reducing the number of variables, reducing your number of features, right? Like, and exactly just as good, Joe. This is literally just the number of features. That's it. It's your number of columns if you're thinking about it in terms of like a, like a spreadsheet, right? So that's literally all dimensionality is. And dimensionality reduction, consequently, is just reducing the number of features. And it helps when I don't randomly invent new letters for the English alphabet. Reducing number of features. So you might ask though, well, first of all, like, why do we do it? Why do we care? And are there any consequences? And so one of the reasons that we might do this is something, an NS Champions 2004. Thank you so much for following. Welcome to the stream. So if we have fewer dimensions, think back to our Neural Nets 101 stream, right? If we have fewer dimensions, right, that could lead to fewer parameters. This is also, you might hear this called degrees of freedom. And if you remember from the 12 Days of Machine Learning Myths, if you were there, fewer parameters helps us avoid the risk of overfitting. When we have a lot more parameters, we have an increase in degrees of freedom, we have an increase in model complexity, right? Then we risk overfitting. So I would say less likely to overfit. So that's one reason. You might also have, computational limits, storage limits. Those might be other reasons to consider some kind of dimensionality reduction. But there are consequences, as there often is in machine learning, right? Everything is a trade-off. And in this case, when we reduce our number of features, when we do dimensionality reduction, sometimes it has the effect of making our models less accurate. Sometimes. Depends. But it's a chance. You run the risk of losing some accuracy because you are, no matter how hard we try, whenever we are reducing dimensions, we are losing information. And so you can do it, if you can do it in a very careful way and, use best practices and blah, blah, blah in the best way possible, maybe you'll lose unimportant information, or maybe you'll lose, only some information, but still you run the risk of losing performance. It might be a very small performance change, and that's kind of that's a trade-off that you have to consider. But also, Ian Alex Hart, thank you for 2 more dog treats. So I think we have 4 now that we have to give them. And so let's see here. Let's talk about principal component analysis. And okay. And Angus the Bus. It's a good name. Thank you so much for following. All right, where do I want to go? I'll go down and then over. My maze-like notes that you all put up with so wonderfully. Okay, so one way that we can do dimensionality reduction is something called principal component analysis, or PCA for short. And again, right? Just to restate though, so it's really, really clear, our goal with PCA is to reduce the number of features while preserving as much info as possible. And AWR417H, R, thank you so much for following and welcome to stream. Okay, so the process here, we're just gonna break it down like step by step. And I wanna use green. And Prebon, thank you for following as well, welcome. Okay, so step one here is, and this is why we talked about scaling, is scale your data. And so in this particular case, we're going to scale via standardization, right? Which is what we just talked about, Strawberry Jesus, I know, right? So in this case, we are going to, and Art of DHT, thank you for following. So standardize, scale your data. And in this case, we are doing this so we know that each of these variables is contributing equally. And if you remember from our long discussion of scaling in the last hour of stream, it's imagine trying to do this. Imagine trying to figure out relationships between your variables and, you know, how much each variable's value is contributing to a label without scaling your data. That's going to be a nightmare. We just learned how much we need to do that. And so that is why our first step is scaling your data. Okay, now step two. Hopefully some of you were here last week for our discussion of covariance, because we're going to use that here. Okay. And so we're not going to go back through the math. So if you are interested in learning about that, I would definitely check out the VOD from last week, or it's also on YouTube. But if you just want to think about it conceptually, it's how much does, if I have two variables, X and Y, and I want to know the covariance of X and Y, it's going to be like, when X changes, how does Y change? How do they vary with respect to each other? And so in this case, what we're going to do is we're going to calculate what's called the covariance matrix. Calculate covariance matrix. And what is a covariance matrix? Well, let's say, I'm going to change colors again. Let's say I have n features, so n number of features. So we're going to end up with an n by n matrix. So for making it easy, let's say we have three features, X, Y, and Z, okay? And then our covariance matrix is going to be like, this would be the covariance of X and X. This would be the covariance of X and Y. This would be the covariance of X and Z. This would be the covariance of Y and X. This would be the covariance of Y and Y. This would be the covariance of Y and Z. And lastly, this would be the covariance of Z, X. This would be the covariance of Z and Y. And this would be the covariance of Z and Z. So obviously I'm not going to write it out for something massive, but this is our covariance matrix. So covariance matrix. Bye, Professor Saucecat. Thank you so much for stopping by. It's good to see you. And let's see here. Whew. One problem with having long hair for the first time is that it gets all over my face and I'm not used to it. Okay. So once we have this covariance matrix, and actually let me clarify something for you here. Is that our covariance will be positive, so will be greater than 0 if there's a positive correlation between the two variables. and our covariance will be negative if there's a negative correlation. Isn't that so nice? That's great how that works. All right. So once we know this, we have essentially a way to quantify how much our variables are how much they vary with each other, how much they're kind of related. And so we can use that in step 3, which is to calculate or determine. I say calculate. Why is there a period after that? Sometimes I just like swap my letters. We're gonna calculate our principal components. Well, what the heck does that even mean? All right, buckle up, my friends, because this is going to be the most complicated part of stream, but hopefully I'll be able to break it down for all of you. So our principal components here. Let's think about. So we have all of our input features, right? We have all of our different features. So like with our breast cancer data set that we were just working with, things like, tumor shape and size. Now we know because we have our covariance matrix, we have a way to kind of quantify some of those linear relationships between our variables. And what we want to do, let's remember our goal, right? We want to reduce the number of variables while not losing a lot of data. Okay, so what are we going to do? Well, principal components. I'm going to write out the definition, and then we'll talk about what it means. And dumb AGI, thank you for following. Principal components are linear combinations of our input variables. So what does that mean? Because that's quite a way to quite a lot of words there. And Rebooting Rocketry, thank you so much for subscribing. Now you've got some cute emotes, and when I get my programmable LEDs working again, you will be able to change all the colors for free, so you can just spam whatever colors you want. And I've got a few other cool sub things that are in the pipeline, so stay tuned. And check out the Discord too. Hopefully you can join the community. Got lots of different channels to talk about everything from cooking and music to lots of different technical topics. So welcome, and yeah, thank you so much for subscribing. All of the support, whether you follow or you subscribe or you give my dogs treats, it really does mean so much, because not only does it allow me to afford new things for stream, like a green screen or the tablet that I'm using to be able to write better notes for you, but it also really helps because I do all of this in my free time, and my weekends and my free hours are often about trying to make stream better for all of you. So I deeply appreciate the support. And Blahman16, thank you so much for following. Okay. I know, Rebooting Rocketry, you say you love seeing the growth of STEM streams on Twitch. Me too. And it's been really, really great. So I've talked about this before, but I streamed video games for the first 2 years of this channel. And don't get me wrong, I still sometimes stream video games because, we all gotta play our games. But, small community. And it was really fun. I met a lot of really cool people. But this year I started streaming science and technology, and it was the impact of my streams was so much greater. And I don't mean how many people were watching. It was just I could reach more people. I could teach something. I could help people. And so it really does have a much greater return for me. But the thing that I've loved the most is just discovering that science and technology community exists on Twitch, and seeing oh my gosh, the people I follow, just the incredible variety of people doing the most amazing things. And I love to tune into just shit that I don't even understand. So I don't know, I follow Deep Sea Jess is a great stream, so if we can give her a shout out. She does she's doing DNA sequencing of deep sea corals, and she'll just stream from her lab, and it's amazing. Obviously game development streams, I gave Jessica Mack a shout out earlier. Her stream is incredible. Just I don't even understand half the stuff she does, and it's amazing. There are just some really, really incredible streams out there. And especially during the day when I'm like having to work and stuff, it's nice to have a stream up and see kind of what other people are doing. I know a lot of you have seen Diatome's Attack in stream. He has a, scanning electron microscope and looks for these little cute things called diatomes. And it's amazing. Like, it's just... When would me in my life ever have access to a scanning electron microscope? Literally never. But thanks to Twitch, I can watch someone using it. And it's so cool. And Lieutenant Lumpy, what a name. Thank you so much for following. So yeah, I completely agree with you rebooting rocketry. It's been great. And I've loved doing these more prepared streams where I've got notes and code for people, but I do want to throw some of the just casual AMA streams in there, because people, sometimes they just want to ask me questions about black holes, and I got you. Like, those are fun too. And it's cool to be able to talk to people about space and tell them all about science. So I'm so glad all of you are here and you enjoy it, because I love it too. Science and tech is awesome. Okay, principal components. What are we even talking about? That's right, linear combinations of our input variables. I need to add something to this. How do I want to say this? What did I say in my notes? I'm usually like far more eloquent when I'm writing this. Combined. So the resulting principal components. I'm going to abbreviate that there just because my wrist is starting to hurt. The resulting principal components are not correlated. So if you want to throw your minds back to one of our early machine learning streams, we all talked about something that I introduced called multi-collinearity, right? And this was a problem. This was something we were trying to avoid and trying to solve in our linear regression. And that was when you have variables that have some kind of linear relationship with each other, in addition to a relationship with our predictor, the thing that we're trying to predict. And so if you remember that, this is kind of intuitive then. So we want to take our input variables and we want to combine them so that we can make some like new fake variables. And by fake, I mean they're just not our input variables. But each of those new variables, let's say new, that's more positive than fake, each of our new variables will not have a linear relationship with each other. They're not going to be correlated at all. And so this is really interesting because the other part of this, I get to fit 3 colors in here, is that, and this is an important thing to remember, is that principal component analysis, when we make these principal components, we try to crams as much info into the first principal component as possible. And subsequent principal components will have less and less information. So what that means is, like, let's say that I have five variables, okay? When I first do the step of principal component analysis, I will have 5 principal components. And this is where things get kind of tricky, all right? Is that what PCA has done is it has taken my input variables, it has combined them in ways that result in 5 principal components that are not themselves, they're not correlated at all with each other. Very, very, independent. But I still have 5. You might ask, like, hey, Jess, I thought this was all about dimensionality reduction. What the heck? Well, remember what I've written in orange. PCA crams as much information into the first principal component as possible with reducing, like, less and less information as we go along. So if I have 5 PCs from my 5 input variables, that means PC number 5, that is going to have the least amount of information in it. So now again, right? I wish that it did it for you, but you have to make the decision as the machine learning engineer how many principal components you're going to have, how many PCs you're going to drop. And yes, unfortunately, no matter what we do, we're going to lose data. We're going to lose information. You just are. You cannot drop whole features from your data set and try to reduce that dimensionality without losing information. But what PCA does do to help you out is it front loads as much information as possible into those first PCs, so that if you're dropping some of the PCs from the end, you're at least dropping the least amount of information. So it's challenging. It really, really is. But so one of the things that and the other thing, I should make a note of this because this is important. One of the downsides, I should write this in red and make a sad face. One of the downsides of principal component analysis is we do lose some interpretability. Because now, instead of having our normal features of, tumor width or shape or whatever, we were looking at earlier, we have these principal components instead, which are linear combinations of those variables, but now they represent something entirely different. And so we lose some explainability, we lose some interpretability when we do principal component analysis. Give me 1 second here. I have a really cool, hold please everyone, because I found this really cool visualization that I wanted to show you. And then when I was trying to reduce the number of Chrome tabs I had up right before stream, I closed the stack of windows with stuff to show you. So give me 1 sec, I'm trying to remember where I found it. And Jasper Acaro, thank you so much for following and welcome to stream. Alright. Oof, okay, ouch. And Lordly Dawn, is there a way to tell how much info we lose for each principal component? Yes. So if you were to, I would say, I'm not sure off the top of my head if scikit-learn's PCA method, which we'll be using today, or class, allows us to do that. Because when I've done PCA, I haven't used scikit-learn's. But if you were to build your own principal component analysis, absolutely. And so that gets into some of the nitty-gritty of how these principal components are calculated, which I didn't do for this stream because it involves some linear algebra stuff that I haven't introduced in Math Monday and will take a little bit of time to introduce. Hi, B4141, welcome. But it involves things like eigenvectors and eigenvalues, which for me brings me back to my quantum mechanic days and makes me very, very happy. But if you haven't done linear algebra, that's going to be it's going to be challenging. And so I will give you kind of like a half answer, which is yes, if you build the PCA approach yourself, and if you're interested in how the specifics of how that's done, stay tuned. But also, can I just point out that some, totally not on purpose, I actually made a rainbow. Isn't that awesome? And just as good, Joe. Okay, is that built into the class? Because that's exactly what using kind of those eigenvectors and eigenvalues will tell you, is you'll be able to see how much variance in your data each principal component represents, which is very handy. So if you want to think about principal components in terms of like a visualization or a geometry, you can think about principal components like directional lines. And thank you for following B4141. So the more variance you have in your data, the larger like the length of the data points along that line. And so what you want to do is you're going to PCA acts like you're going to be rotating your data set. It's almost like a transformation of axes. So if ever you've done moving from XY axes to polar coordinates or something, it kind of works. Visually speaking, you can think about it like that, where you're going to define new axes for your data set that are these principal components that lie along the greatest areas of variance in your data set. And Klaus Dev Walker, thank you so much for following. And to help explain that, I found this really, really cool visualization. Thanks to Zakaria Jadi for creating this, but it's a visualization of what is happening a little bit with principal component analysis. And so you can see here's our like normal XY, but you can see that the line that lays along the purple actually is going in the direction of the greatest variance. And so our first principal component would be that, like, along that line. And so you can see that, you know, as we're, and our second principal component, right, we want it to be entirely uncorrelated. We're dealing with linear combinations. So those of you who, hopefully this is like tingling your math brain, and uncorrelated in a linear sense means perpendicular. And so our next principal component would be perpendicular to that purple line. But obviously, when we're dealing with tens of thousands of features, it's a little bit more complicated than just two features, two dimensions, right? We're dealing with high dimensionality data sets. And Ian Alex, thank you so much for 2 more dog treats. So when we take a break, we'll see if we can stuff the dogs full of more dog treats. I think we're up to 6 now, six dog treats. So thank you so much for the bits. And so that's really what we're doing is we're recasting our data along new axes that lie in the directions of greatest variance. And there are some challenges that come along with this. So actually, before I keep blabbing, let me write step 4, which is just, hi C Films, how are you? Oh no, where did green go? Step 4 is just gonna be recast data given the new PCs. Okay. So let's do this a little more practically. So let us return to our data. And we'll zoom back in. Ooh, that's too large. There we go. All right. And so if you remember from our cancer data earlier, we're gonna have 30 features. So honestly, is this like the greatest use of PCA? Probably not. Like 30 features isn't a whole lot, but we're gonna use this because it's gonna be snappy, it's gonna be quick, and it'll be good to illustrate what's going on. So first, what I want to do is I'm gonna show you one of the ways that we can look at figuring out what features might be irrelevant. And C Films, you say, how is the teaching of data science fundamentals? It's going great. How are you doing? What are you up to today? It feels weird to call this cancer, but whatever. So also, huge shout out to, what is it called? It's an O'Reilly book, Introduction to Machine Learning with Python, because they have some really wonderful visualizations for your most common data sets. So the data sets that you all are probably familiar with from Machine Learning Miss, Boston Housing, our Iris data set, Titanic data set, they have some great visualizations. So I got this visualization from that because I hate visualizations. So actually, I'm just gonna copy it real quick so that I don't have to write out all this code. But huge shout out to them for this because I hate making visualizations. So, and hi 3rd tier gaming, and C Films, I'm using Python. So, there we go. All right, so let's talk about kind of what we're looking at here. So we are looking at different distributions of features by our labels. So we have malignant and benign, which the colors are swapped, but that's fine. And if you think about it, right, what we want is we want features where the distribution of that feature for our malignant tumors and the distribution of that feature for our benign tumors is very, very different, right? So something like mean concave points, whatever that means. This is great. This would be great for helping us figure out what's a malignant tumor versus what's a benign tumor. Because look, like there's very, very little overlap. So tumors that have, this value maybe of 0.06, right? They might be either one. But if you have mean concave points of 0, those are all benign tumors. Unfortunately, things like mean symmetry or mean smoothness, they have so much overlap that these particular features aren't going to be as useful. We're not getting that nice division between our different groups. So let's do some PCA now. Actually, here's another great, error, but hold on. Worst radius, look, this looks like another good one. Worst smoothness, this looks less helpful because we have more of that overlap. And so that's, in some ways, that's really what PCA is going to be doing, is when we talk about how much information does a particular feature hold, one thing we're looking at is stuff like this. Look at worst concave points compared to worst smoothness. We would say that worst concave points holds a lot more information than worst smoothness, because worst smoothness, it's not going to be helpful in distinguishing between our malignant and our benign tumors, whereas something like worst concave points absolutely is. So hopefully that gives you some intuition. What did I call our data? Yeah. And then, all right, so let's do that. And so for this, I'm going to ask for 2 principal components, just for the sake of visualization and easiness. I would say that a lot of times you're going to start with a larger amount, evaluate how it's doing, and reduce based on that. But in this particular case, because I would really like to be able to visualize for you what's going on, we're going to be using 2. And hi, Marco Dev. Welcome. How are you? How are you doing? Transform scale data. And here's one of my crappy visualizations just for you, just for all of you. I wish I had. I don't know why I dislike visualizations so much. They're so important, and people who can do them well have such a gift, and I just don't like it. Hi, Smallsy! Hey, how are you? Can we get a shout out for Smallsy? So those of you who were, okay, and because I spelled this wrong. Hold, please. Oh, this is PCA data. Sorry, hold on. Shout out for Smallsy. Those of you who saw the panel last night. This is Smallsy from the panel. A wild Smallsy appears. That was so much fun being on the panel, wasn't it? It was great to meet you too. So I'm glad that you have showed up. Wait. Hold, please. Excuse me. What? Give me a second. Hold on. I didn't have to do the colors. They worked last time. Hold on. I'm gonna just do the. Nope. All right. Hold on. 1 second. Literally, when I did this, same like line for line, same code. No. Hold on. I did it wrong. That's why. Always. That's it. I am such a doofus sometimes. Okay, hold on. There we go. Yeah, I fixed it. And it was so much fun. Yes, it was. So we were on a panel talking about access and gaming, and so it was really great. And I always love to get connected with the community because it's like when you're not in that community, you have to work so much harder, I feel like, to either to fit in or to literally access things, so that when we're all together and we're getting to talk about these issues, it's like just the stress level for me goes down a little bit. Like I'm far more comfortable than I am normally. So it was a wonderful experience. Check out Stream Queens. The VOD is there if any of you are interested. It was a wonderful con. So there was a panel on intersectionality before that, and then we all played Among Us. I played Among Us for the first time, so I was very bad at it. But okay, so what you can see here is our, we're plotting our two principal components, and what they've done is they've almost perfectly started to pull that data apart into the two labels that we're looking at. Isn't that awesome? Like, it's already starting to draw that division between our classes that we wanted. And this is going to start to help you get ready for the model that we're going to talk about. Oh, Smalsy, wait. You say you're streaming tonight? I can raid you if you're... When are you streaming? Because if you're streaming if you start streaming at least when I'm wrapping this up, I'll raid you. But okay, so you might oh no, like tonight Australian time. Oh, okay, well. Wait, isn't it like 12-hour difference for Australia? So you're talking about like in literally hours and hours and hours. So never mind. Prebon, thank you so much for subscribing. Thank you so much. And I'm so glad you're enjoying stream. As I've mentioned before, all subs and follows and bits and all of that, it's so very welcome. It means a lot to know that like the tutorials I'm doing and the content I'm making for all of you is that you enjoy it. So thank you. I really appreciate the sub. Oh my gosh, 4 or 5 a.m. No, I will be done way before that. I have to get up very, very early for my vaccine. So, oh, Lovebone, thank you so much for gifting sub to Smallsy. So now, Smallsy, you get a cute emote of my dog. I think you get 2 actually, and a burger. But you get 2 cute little things of my dogs. And like I mentioned earlier, once I get my programmable LEDs fixed, another cool sub perk is that you can control the colors of the LEDs. So, yay. All right. So the machine learning model that we're going to be talking about tonight is something called support vector machines. And I want you to fix this. Dog break. We need a dog break. We do need a dog break. I'm so sorry. Yes. Let me get that set up. 1 second, please. Okay. All right. It's almost set up. There we go. All right. So this is my dog Hubble. And I think we have 8 treats. Lordy. Does he want... Oh. Is it going to spit out treats for him? Did it? Yes. There we go. All right. So look at... This is my boy. It does shoot out 2 at a time. I know. Okay. So those were 2 treats. Now he gets 4. I know how to count by 2s. I was trying to spoil him, but I see how it is. Oh my God, he's such a good boy. So all of your bits and everything goes towards giving the dogs more treats. So that's 6 treats for Hubble, and then we'll do 1 more set. So, oh my goodness, Worsher, thank you so much for the sub as well. Yay, that is awesome. Thank you. You all are so wonderful. Sub's just like, it's so sweet. Like, thank you for supporting, like, of all things, to support my stream. I don't know, it means a lot. All right, 8 treats for Hubble. So also frequently, it depends on his mood because he is a bit of a diva, but my other dog, Tennessee, sings for all of you. Yeah, okay, Lovebone's beating me to it, but Tennessee loves to sing to sci-fi themes for TV shows. So if we have time and Tennessee is feeling like it, at the end of stream, everyone votes on the song Tennessee should sing for you, and then he comes in and he sings. So hopefully some of you will be around for that. It's very, very, very cute. Okay, so we'll say bye to Hubble because he's gotten his 8 treats. Good Lord, so many treats. And let's talk about support vector machines for a sec. So let me also find out where I need to, like, okay, we'll put it over here. Making sure I got the room. All right, put it like here. Oh, yay, I'm so glad, Smallsy. Okay, well, also I don't want to interrupt your work, but I know that life of having a stream up while you're working. It's kind of fun. All right, so where did I put my stylus? All right, support vector machines. Again, kind of sounds a lot more complicated than it is. Wait, did I skip? No, I didn't. Okay, we're good. All right. So, okay. Support vector machines. We are talking about, so this is a supervised learning model. So those of you who have been here for the previous machine learning streams know that supervised learning means that we have labels that we can train on. And wait, what? Third tier, you say no alert for third tier? I feel like this has happened before, hasn't it? Or like it was like super, super delayed or something. Like it took like a lot longer and I have no idea why. In addition to being a supervised learning model, it is it's a classification model. Oh my goodness! Loafbone, what are you doing? Stop that! Oh my goodness! Thank you. Now we have a hype train, but also Kangaroobin, Ori Concept Arts, Brethren, Sportac77, and Cattle Co. Welcome, you all have subs now. Thank you, Loafbone. You and all of your subs. Oh my goodness. It's no burger. I'll have to look into that. That's weird. Whoa, that's a lot of hype things. But the hype train is continuing to go. So, does it give you I thought it gave you the hype things at the end. Okay, I still don't understand how these work. But anyway, thank you so much, Loafbone. That's really sweet. Thank you so much for the gift subs. And I'm so glad everyone has, you all have subs now. Working on, so I'm finding an artist to do some more cute like emojis and stuff so that we'll have some more cool sub rewards and everything as well. So also now that I can play Among Us, kind of, maybe we could make that like another reward of some kind, or like a sub perk is that there's like an Among Us game with subs every once in a while or something. So we're sure, yeah, I know. It's my favorite things in the world, my dogs and a cheeseburger. So, but I want to get some more. I want to get some more cute emotes. Third tier, thank you so much. Left 4 Dead 666, what a name. Now you have a sub to the channel, so thank you so much for the gift subs, guys. You all are so sweet. Thank you. Now I'm getting all flustered. I'm just trying to talk about support vector machines. That time it worked. Yeah, who knows? When I hover over, I see you've got like the like badge and stuff. So who knows? Twitch is sometimes very frustrating and glitchy. Okay. So if you recall what we just saw, what were you talking about? See, I got all flustered. Let me draw a pic. Oh, that's bad news. All right. Okay. I'm making an example for us here. Okay. Let's say this is our data. And these are our two classes. Well, support vector machine. Oh my goodness! Oh, wait, there we go. Now your thing came in. It just took a minute. Sometimes it's really slow. But thank you so much, third tier, for resubscribing. Yeah, you've got like the 3-month sub badge. So thank you. I also want to make cuter sub badges too. So also thank you, Twitch, for taking forever with that. But in any case, Rocket Sage, hi! I love your stream. Thank you so much for following. So actually, Atomic Schools, you say linear regression. Linear regression is not what we want here, because linear regression, we are trying to classify like a kind of like a 2 categories here, or 2 classes. So a linear regression wouldn't really fit. We need Enceladus for multi-month stuff. Yeah, we need some cute like Enceladus. Also, I feel like so many people have like cute like facial, like not my face, but like whether it's the dogs or it's maybe Enceladus or something, like they have like different face expressions. So you can like have something where someone's upset or like something where they're like really excited or something. So I think that could be cute. In any case, we have 2 classes here. So for this particular example, for my drawing ability, we have 2 classes. And so what a support vector machine model is going to do is it's going to try to draw or determine what's called a decision boundary between our classes. And so in this case, like we might, if it were you or me, we might say, all right, let's draw, oh gosh, me in straight lines. Let's say, maybe this is my decision boundary, right? Because it separates my data into 2 categories. And if it's 2-dimensional, then we can do the 2. Yay, hype train success! What's my emote? I want an emote. I like that with a little arrow. That's a cute, that's really cute. Okay, and then Art of DHT, you say, a question. If I want to build a machine learning model algorithm for determining transits around stars, what classification would be best? So let me think. That's different because it's not necessarily, I wouldn't do a classification model there because you're not trying to necessarily classify, well, it depends. What kind of data do you have? So if you're talking about, you know, me coming from astronomy, the data that I typically deal with when it comes to finding exoplanets is going to be, it's going to be what's called transit data, which is you're going to have something that kind of looks like this. And so this is, you can think about this as like almost kind of like the brightness of your star. And this is time. And so when you see that, ooh, normal brightness in our star, and then it goes whoop like this, that's because a lot of times something is passing in front of that star and it's lowering the brightness of the star from our point of view. So really though, if like a classification model wouldn't really work here. It wouldn't really work for time series data, not in this sort of sense. So I would, in that case, there's a lot of really, well, okay, so I should also clarify that one of the things that makes exoplanet detection so challenging is that, you know, you very rarely do you have a system that is a single star with a single planet, and that's it. So you have multiple planets, you have planets with moons, you have, you know, all kinds of dynamic, interesting things that happen and can overlap. And so I've seen some really cool stuff though, Art of DHT, doing like some Bayesian process modeling with exoplanet detection. So that could be really, really cool as well. It should look for periodic drops in brightness with the same amplitude, but a lot of times that's going to be masked. So like, again, pardon the drawings, but if this is the brightness of our star, right? So I'll just star. And maybe this is like the average brightness. Well, first of all, we're making the assumption that our star isn't variable. So that can be really, really troublesome when you also have a star that has variability as well. But like maybe you have, all right, maybe you have one planet that transits like this. Then you have another planet that is transiting like this. Then you have another planet that is transiting like this. And when you have all of this stuff all overlapped, it can become incredibly difficult to like extract the all of the different variations that's happening, especially if you have something that is like a very long period planet, because then it might only come up once in your transit data. And also those beautiful curves I was just drawing, assume that you have that much data from each of those nights when oftentimes you don't. It's going to be a patchier curve. So you're going to have missing, like, you want to talk about the missing data problem, look at exoplanet detection. Assayus, thank you so much for following and welcome to stream. Okay, so back to SVMs for a second. Right, so this is called our, oof. That got, no. What is happening? Go away. You go away, and you go away. Okay, so this is what is called a decision boundary. And in this particular case, we're very, very lucky because our data is what's called, it's linearly separable. Why is that popping up again? Go away. Oh, it is struggling. All right, please go away. All right, and linearly separable because it is able to be separated by like a linear function. And so the goal of an SVM is to output this decision boundary. Now in 2 dimensions, yes, we're just talking about a line, at least in this case so far. But when we get to larger and larger dimensions, we're talking about a plane. And you might ask, well, how do we find the best decision boundary? Well, so, I finally get to use my highlighter here. The SVM does that through something called margins. And so margins in this case are going to be the distance from each from each class, like each item of the class to the line. And so in this case, if we had, say, a line here, this would be a very bad decision boundary. It still would be effective, but it wouldn't be the optimal decision boundary because it's not maximizing the distance from each of these, each of these blue points and each of these red points to the decision boundary. So we really want that margin, the distance, to be maximized. So, like I said, this example, our data is linearly separable, which is wonderful. Oh, easy peasy, right? Like, unfortunately, though, as we all know, especially from lots of my streams, is that real life is a lot more complicated. So, like, what if we have the example? Drawing data is such a pain. Right. What if we have this kind of example? Well, if we try to draw a line to separate this data, we can't. So do we just give up? Is this like a limitation of SVMs? Are we just, sad face, we can't do anything? Well, no. So this is where SVMs can do really, really cool things. Is what an SVM is going to do is it's going to add another dimension. And so we're going to add a third dimension to this, like that. And perhaps we're going to choose this dimension in a way that is helpful. So in this particular case, we might say use the equation of a circle and use like maybe the radius of the circle or something. And so what's going to happen is it's going to pull out and separate our 2 classes of data. And now I'm a terrible artist, so have no fear. I found a YouTube video that itself is not very high quality, unfortunately, but kind of gets across what I'm talking about. And so don't worry so much about the text. I'm gonna go through it with you, but watch the visualization. So we started out with kind of a similar thing to what I drew. And then it's going to add that third dimension, and we're going to be able to find a plane because we're dealing with more than 2 dimensions. We'll be able to find a plane that does separate our data into the 2 different categories that we're interested in. And so this is a really interesting way that our support vector machine can handle non-linearly separable data. So I will post the link to the YouTube video in chat for anyone who is interested. And you know, this is great. This process of adding dimensions is cool, right? But also, aren't we talking about dimensionality reduction? We know the danger of adding dimensions. And especially if you're thinking about, you know, a really, really complex, you know, distribution relationship of features, then things could get really messy. Well, have no fear. So SVM has a couple tricks up its sleeve. In particular, it has something called a kernel trick. And this is the fact that it's going to use, let's see, SVM uses dot products instead of the actual vectors themselves. So instead of our feature vectors, it's going to use dot products instead of entire vectors. So that's great. That's going to help us with the fact that we're adding dimensionality. So we're adding, you know, computation and complexity and all the stuff that we usually try to avoid. And it's called Kernel Trick, by the way, because the formula that we use to add that additional dimension is our kernel function. Okay, but enough blabbing about it, right? Let's build it. And Atomic Schools, you say just throw a neural net at it? No. Neural nets are not the answer to everything, unfortunately. Okay, so let's zoom in on this. Okay, so we're going to use our same data set. SVC. Oh my God. Support vector classifier. Whoops. All right. And we are going to scale our data. Almost always scale your data. Oh, what did I call it? There we go. All right, so we're just going to use out of the box, really, really simple SVC, support vector classifier. And we're going to fit it to our test data, or sorry, to our train data. I am swapping all kinds of things today. So we get a really good performance out of this. And they are wonderful classifiers. They really, really are. They do well on both low and high dimensionality data, but they do struggle with some things, okay? And because we are adding that layer of dimensionality, we're adding extra dimensions to our data. It means that even with the kernel trick, unfortunately, if you start to get high volume data, an SVM is just not going to perform as well. It's really going to struggle. You're going to, you know, you're adding in a lot of computational complexity. And similarly, you know, this entire stream has largely been about preprocessing, and SVCs require, or SVMs require, very, very careful preprocessing, very careful tuning. They're a lot more finicky than some of the other classifiers we've used, and for that reason, you see them used less compared to other classification models like, you know, decision trees or random forests, right? Like, so I think they're interpretable, they're explainable, and there's cases where they perform really, really well, but they are a little bit more finicky. And oh my goodness, Atomic Schools, Alsa Joga and Monkey Patcher, thank you so much for following. And Strawberry Jesus, you ask, what is the kernel trick again? So that is the fact that a support vector machine uses dot products instead of the whole vector itself as a way to kind of save some computation. And okay, so Pawn Noobs and Winyo, you ask, is the parachute looking thing gradient descent? No. So In this particular case, that parachute looking thing was us adding a third dimension to be able to separate our data into classes. And so if you look back here, we can't draw a line. This is not linearly separable, but you can imagine a case where if we add a third dimension, that red data sinks to the bottom and we're able to have a plane that separates it instead. So it's not so much dimensionality, Strawberry Jesus, it's volume. So on high volume data, yeah, it does not perform as well. But all right, so to kind of review a little bit of what we've talked about, we talked about preprocessing, so we talked about scaling and dimensionality reduction, and we talked about principal component analysis, which is a very common way to approach dimensionality reduction. And I gave you a very quick introduction to another kind of classification model that we didn't actually cover in the 12 days of machine learning myths, which are support vector machines. So hopefully all of this has been interesting and fun. Tomorrow, I believe we have, if all goes well, so I will say this, is that tomorrow I have my second dose of the vaccine. And so I've heard that dose 2 can be a little bit rough. And so hopefully if it doesn't affect me, then we will have our first Math Monday stream tomorrow. If it hits me like a truck, like dose 1 did, we might have to start Math Monday next week, unfortunately. And I know a lot of you are waiting for Math Mondays, and I'm really, really excited about Math Monday. I can't wait to start those streams, but I know at least for me, the first dose of the vaccine really took it out of me, and so I will not be teaching you very well. I won't be explaining math very well to you if I try to do it when I'm all loopy from the vaccine. But okay, and yes, Strawberry Jesus, absolutely. That's a good way to think about it. That's why I kind of linked those two together. But before we wrap up, are there any other questions? Are there requests for future topics for the fundamentals of data science? Because I think with the 12 days of machine learning myths, I knew how many days I wanted to do, so it was really easy to sit there and go, these are the 12 topics. But for the fundamentals of data science, like this is as broad as we can make it, and so we can do whatever topics interest people. And Strawberry Jesus, you say deeper dive on dimensionality reduction. Sure. Okay, so I will make a note of that. Here's my notes. Let's see, suggested future topics. Deeper dive into dimensionality reduction. Okay. And of course, Lordly Don, I'm glad that you enjoyed the stream. If you enjoyed this though and you found it helpful and you want to learn more about machine learning while waiting for next week's stream, I would recommend checking out the 12 Days of Machine Learning Myths on YouTube, because that is I went through a whole lot of machine learning there. So hopefully that can whet your appetite in the meantime. So I usually do Science Sundays. So this is when I'm going to do streams on data science, machine learning, sometimes astrophysics. Math Mondays are coming soon. That's something I've been kind of like spinning in the works for a while. Tuesdays, I try to do like a viewer's choice. So if you notice in your channel points redemptions, you can redeem a science topic or you can redeem a game. And so that's when those redemptions happen. Thursdays, I'm learning game dev terribly, but I'm learning it nevertheless. And then next Sunday, of course, we'll have another Science Sunday. So I am gonna find somebody for us to raid in the meantime. And let's see. Okay, ready to say hypothesis testing. Okay, I'll add that, hypothesis testing. What about doing more Python programming learning streaming? So I could do a series on programming. Maybe it would be good to do for the fundamentals. I could do like like good, like maybe like Python tools for data science. So we could like go over some really common libraries or tools. Oh, what is this? A straw poll? Is this for Tennessee singing? No, wait. Oh, Volcano Doc is live too? Okay, let me see. Oh, thank you. Okay, I was like, what? What the heck, straw poll? Tennessee. Okay, so also for those of you who are new to stream, my dog sings. And he likes to sing for you. He's so excited. Seriously, you all. Like, on days where I don't stream. No, even on days where I do stream, when I'm in my office for an extended period of time, like, you know, having meetings or something, if he sees me leave my office, he thinks it's time to sing. And he gets so frisky and he starts like running up and down the hallway, getting really, really excited. And I'm like, Tennessee, it's like 2 p.m. I'm at work. Like, you're not going to be singing right now. But he loves singing for all of you. Elmer's Adhesive, thank you so much for following. So please vote. Please vote for your for the song that you would like Tennessee to sing. I am gonna go get him. And let's see. Thank you also Ali Yager 7 for following. And a series on data types. Okay, I could see that working. And let's see here. So I am going to be right back. And Blobman, no worries. Don't worry if like oh no, I've got my voice coming back at me. Ugh. No worries if things, you know, you don't understand things. We're gonna have streams that are more aimed at beginners. Definitely check out the first few days of machine learning myths, because I think I took those days particularly, like, it's great intro level stuff. And then there's gonna be streams where we're gonna do like more advanced things. So don't worry about it. But let's see. Okay, I have to take down the green screen. So I'm gonna be right back. I'm gonna run an ad in the meantime, because I'm supposed to do that apparently. But I will be right back, and because also I think it disables ads for people jumping in. I'm gonna get Tennessee ready. I'm gonna get his treat. I'm gonna take down the green screen. I will be right back. All right, friends. Okay, so I have to adjust a few things. So let me see. What are the results? DS9 and Voyager are tied. So if you all can vote, please. Let's resolve the tie while I am fixing the webcam. Because I got to remove the crop so that all of you can see Tennessee. Oh, I know, Ten. They're gonna see you. Don't you worry, Bat. Don't you worry, Tennessee. I know, you're so excited for songs. You're so excited. I know, sweetness. Okay. Let's set up this mic so that you all can hear him. There you go, Ten. Let's adjust this. Okay, you're a good boy. All right. There's cheese for you. All right, DS9 is pulling in the lead, so I'm going to give it just a couple seconds left. I know, Tennessee, can you come over here, Matt, so people can see you? There you go. Oh, you're such a good boy. Oh, I know, you're so excited. You're so excited to sing. Oh, my goodness. Tennessee, tell me all about it, Bat. Tell me all about it. Oh, yes, I know. Okay. DS9 it is. All right. Okay, Tennessee. There's no song yet, 10. You gotta wait for the song, Bat. Star Trek. DS9 theme. Volume warning. I'm gonna turn down the mic. But little Tennessee. There's no song yet. Okay, Bat. 10, Tennessee. There's an ad, Bat. You have to wait. Oh shit! It's connecting to my headphones. Hold on, 10. Hold on. Okay. All right.
Turns out love's kind of inexpensive.
Oh, I know. No, there's no. Hold on, 10. Here you go. Here's your song. Tennessee. Gotta wait for your song. Shy, I'm sorry. I didn't mean to laugh. You're a good boy. Oh, that was such a good song. I'm sorry I laughed at you and threw you off. Oh my goodness, here you go. You're a very good singer. Everyone loved your song. Everyone loved it, I promise. You're a very good boy. Oh my god. A raid! Oh my goodness. What interesting timing. Hi everyone. Raiders, you just missed my dog singing for you. So, hi, Ted, come on. Yeah, hi. You're a good boy. Hi. I love you. So this is Tennessee, and he sings to sci-fi themes. Hi, you're very good. I'm out of cheese, Bat. I gave you all of your cheese already, sweetness. Well, thank you for the kisses, though. This is very sweet. But so he loves to sing sci-fi TV show themes for everyone. He's quite talented. He loves it. It's his favorite thing. He's been waiting to sing to all of you for all day. He needs to sing for the Raiders. Okay. Well, Raiders, you're going to have to tell me what you want. So he can sing, he just sang DS9. He can sing Voyager. He can sing TNG. He can sing SG-1, so Stargate SG-1. He can sing Stargate Atlantis. Okay, well, yes. Okay, Voyager was second, so let's do Voyager. Also, because Voyager's awesome. Okay, Tennessee, would you like to sing again? I don't have any treats for you, but you love singing so much you'll probably do it anyway. Little bit of a volume warning. He gets loud, but this is for all of you Raiders. Okay, 10. Okay. Can you come over here, Bat? Good boy. Sit. Are you going to sing for everyone again? Because you're a good boy. You're good. It's okay. That was a very good song. That was a very good song. Good boy. Good boy, sweetheart. That was a very good song, Tennessee. A very good song. Hi, Tennessee. Tennessee. Are you so excited? He loves to throw his paws up when he's excited. Tennessee. Tennessee. Tennessee boy. Are you a good boy? Yes, you're a very good boy. Hopefully you all enjoyed that. Yes, so he's a very good singer. He's a very good boy. He will listen, and so like you'll hear him kind of like tilting his head and like listening to what part is coming up next. He also has favorite parts of songs. So there's particular parts in each of the themes that he likes where he gets really overwhelmed with how happy he is about the fact that it's a certain song and it's this certain part. And he just like, he'll preempt it sometimes. So you'll see him and he like, especially if you know what his favorite part is, it'll be like a second or two before the favorite part starts. And then he'll just throw his head back and start howling. And especially for the song that he was singing before this one, he was howling so intensively that like, his little front paws were coming off the ground. So he loves singing for all of you. He gets so excited when it's, you know, that time, and he knows, like he sometimes thinks it's time and it's not time. But so thank you all for giving him an audience. He's quite a diva. But it looks like I missed lots of follows here. Thank you, Glowfly22 and Devil Honor and It's Luku and Cootie Juice for following. You all missed a little bit of the stream, but have no fear, the VODs will be up on YouTube. This is part of a series of streams I'm doing on Sundays called Data Science Fundamentals, and I'll be covering a whole wide array of data science fundamental topics. So today we talked about data preprocessing. We talked about scaling, different kinds of scalars and how to scale your data. We talked about dimensionality reduction, and I went through what principal component analysis is. And then I introduced a classification model that I haven't done on stream before, which is a support vector machine. So if there are any topics, though, people want to hear about, they want me to do streams on, I have a list going. So let me pull that up really quick. Looks like so far people have asked for a deeper dive into dimensionality reduction, so more methods for dimensionality reduction. Someone asked for hypothesis testing, and then more Python tools for data science. Cicero writes, and Death God at 1206, thank you for following. and applications of math. So Devil Honor, I'm starting a series of streams on Mondays, Math Monday, because we've got Science Sundays, and then we're gonna have Math Mondays. And so that would be a great stream series for me to cover math applications. And we'll do statistics, we'll do a variety of math topics. But specifically, I would say for data science and machine learning topics, I'd love to know more about what you all want to see. Here you go. Everyone can see you still, 10, because you're a very cute boy. And atomic schools, so I used to do more astrophysics on Science Sundays, but so I'm going to be balancing the astrophysics streams, like the kind of more casual streams that I do, where we do kind of like a Q&A, or I pick a particular topic and we just casually talk about it. I'm going to balance those with these fundamentals of data science streams where I'm doing like more prepared stuff. Yes, and also Love Bone is right. This entire giant bed here is for dogs, solely for dogs. But if there are astrophysics topics that you would like me to do a deeper dive into, hi Bat, you're very cute. Just let me know, and I can add those to my list. And Prebon, you say self-learning, I'm guessing you also mean reinforcement learning. So I actually did a whole series, 2 videos on reinforcement learning. So you can check out YouTube for that. I did an intro to reinforcement learning where I talked about Q learning. And then I did a follow-up for like intermediate level reinforcement learning where I talked about deep Q networks and policy gradients and actor critic models. Byte push array. Thank you for following. And Devil Hunter, that's fine. We talked about gradient descent in the 12 Days of Machine Learning Miss. So like that's totally fine. Honestly, that's why the 12 Days of Machine Learning Miss series on YouTube is out there, so that I can give people kind of a whirlwind tour of a lot of different data science things and machine learning topics. So if you all see stuff in those videos and you're like, I want to learn more about this or do a stream on this, like please do let me know, because especially given that I do this every day, sometimes what the fundamental topics are, I can be a little bit removed from that, just because like it's sometimes hard to remember the things that you didn't know, if that makes sense. And so there are topics people want to hear more about, or things that you don't see people doing these tutorials, like you struggle to find walkthroughs or code to help you with something, just let me know. And do I know about variational autoencoders? A little bit. I've built a few. That was, what year is it? It's 2021. So that would have been like 2.5 years ago. But if that is a topic of interest, like I can definitely add that to the list of topics for sure. And Devil Honor, you asked about my transition from astrophysics to machine learning. So I would say that I had a lot of the math and the stats, and that made learning the machine learning a lot easier. But I hadn't done machine learning for Astro really. I'd done like a little bit, but not much. So a lot of it was me teaching myself. And so teaching myself Python and programming, and also teaching myself the machine learning. And Super Bueb, thank you so much for following. Yeah, thank you for the shout out for Tayo Inoue, Loafbone. It was so wonderful to raid. Hopefully, I got really excited, so I hope I also thanked Tayo Inoue at the start of the raid. But if I didn't, another thank you. I know we've been trying to raid Tayo Inoue for a while actually, but I think our schedules don't really fit as well. And Blahman, you say, I find this very informative. You think it will be useful? Good. You ask, do you have to do the math or just plug it into Python? Well, if you're asking me personally, a lot of times I'll use libraries in Python that already have certain model types if it's a model type that is very common. I've had to build like some architectures that are more complicated, especially when you get into like deep learning and you have architectures that are very complex. Sometimes I've found that it's, for me at least, for like at the very least the learning value, it's really helpful to just build some of that from scratch. If you're asking, generally speaking, should you learn the math? My answer to that is always going to be yes. You should always learn the math. Also because when you are building these models, you should understand what they're doing. You should understand why the models are doing what they're doing, what the math is behind the model. Even if you don't like have to, derive the math and like calculate it every day or something, it really does improve your knowledge of the topic. And Devil Honor, you ask, what is the difference between machine learning and neural nets? So neural networks are a type of machine learning model. And so there's lots of different types of models and different approaches to machine learning. Neural nets are one of them. I also did an entire video on Neural Nets 101. So if you're interested in neural nets and you're like, oh, I don't know, the math is scary, I'm like not ready for this, I would check out that video. It's a really, really simple introduction. And we actually build a really basic neural net from scratch in Python. So we don't we don't use Keras, we don't use TensorFlow, we did it all ourselves. So that would be, if you're interested in neural nets, I would recommend that because we went through it in detail. But let's see here. Did I miss anything else? Don't think so. But neural nets are really interesting because they can be very powerful, but you sacrifice a lot of interpretability because I think not a lot of people actually understand like deeply what the neural nets are doing. A lot of folks will just kind of plug stuff into them. So it's really cool. They're very interesting. And if you are interested in learning more, I don't know the YouTube channel you're recommending, Atomic Schools, but of course I'm going to shamelessly plug the 12 Days of Machine Learning Myths video on Neural Nets 101. But in any case, let's find someone to raid because also I have to get up super early for my vaccine. So I'm going to be a responsible adult. I'm going to go to bed on time. And hopefully depending on how things go, we can maybe have Math Monday tomorrow. If the vaccine thwacks me in the back of the head and I'm really tired, then we'll wait for next week. But let's see. I want to give love back to Volcano Doc. She has rated me previously. She's a volcanologist studying volcanoes, so I'd love to pay it forward a little bit, raid back. She's really, really cool though. So you can ask her all of your volcano questions. But I will see you guys hopefully tomorrow. If not tomorrow, then I'll see you later this week. Be sure to join the Discord though for updates on streams and everything. But I will see you all next time. Have a good